Hello, dear viewer of my channel. We have an urgent news release that won't leave you indifferent. I'm glad to welcome you to this video. Make yourself comfortable while I begin my message to all of humanity. You think radio noise is random? Not at 142 megahertz. Tonight the carrier locks on 3i Atlas and the interval snaps into a rhythm with odds around 1 in tens of thousands. Think about that. If a structured signal sits on the hydrogen line, you don't get a do-over. Multiple observatories confirm it. Same frequency, same timing, but here is what is strange. The intervals line up with Earth. We follow the data, not the press releases. The timing is not accidental. By the end, you'll see why October 29th, 2025 isn't a date. It's a countdown measured in hydrogen's heartbeat. Let's start with what's moving through our neighborhood. 3i Atlas is an interstellar interloper, the third confirmed object not bound to our sun, passing through our system on a one-way track. It isn't from here. Its hyperbolic path tells you that. The speed, the trajectory, the way its course refuses to close into an ellipse. This is a visitor crossing the ecliptic plane like a coin skimming a dinner plate. We've seen this pattern before with two earlier interstellar objects. Each arrival forced us to adjust our assumptions. This one adds something we didn't plan for. A radio heartbeat sitting on a frequency no one picks by accident. 142 megahertz is the neutral hydrogen line. Hydrogen's ground state spin flip transition emits at that frequency. In plain language, if the universe has a universal channel, this is it. Hydrogen is everywhere. The line is narrow, clean, and cosmically meaningful. For decades, SETI projects have watched that band because it's the obvious rendezvous point. You could search the whole dial, or you could call on the one channel a physics-literate civilization would expect. The timing is not accidental. But here is what is strange. Natural astrophysical sources do produce energy near 142 megahertz gas clouds, the galactic background, but they don't hold precise, stable, narrow band pulses that repeat with low jitter and fixed phase like a metronome. Natural lines broaden. They wander with thermal motion, turbulence, scintillation through the interstellar medium. They don't come pre-packaged with a clean carrier and symmetric sidebands. They don't wait for our telescopes to line up and then snap into a sequence that echoes our orbital dynamics. A comet with a radio tail is not a clock. A gas cloud is not a countdown. Geometry matters here. When you steer a radio telescope, you're aiming a narrow beam at a moving target that's itself crossing the sky at an angle, Doppler shifted by both its motion and Earth's rotation. If you claim a signal is co-located with 3i Atlas, you need to show the beam center, the antenna pattern, and the side lobe suppression that keeps terrestrial interference from sneaking in. You need astrometric alignment within the error ellipse. You need to apply the right Doppler correction so the tone doesn't drift out of the band as the Earth spins and orbits. If after all that, the tone stays where physics says it should, that's not a casual anomaly. That is design-level stability. Let me explain why that matters. Stability implies an oscillator with a reference. On Earth, we anchor to atomic clocks. In space, you can do the same, or you lock to a celestial constant. The hydrogen line serves both purposes, a frequency any scientist can find and a symbol encoded in the structure of matter. If you wanted to announce presence without language, you'd use a line that every chemistry student recognizes. You'd keep it narrow to beat the noise. You'd bake meaning into timing, not just tone, because time ratios are unitless and immune to unit confusion. That choice isn't decoration, it's intentionality. So we ask harder questions. Could scintillation, the twinkling of radio sources through turbulent plasma, fake a pattern? Scintillation creates amplitude fluctuations and can create apparent intermittency, but it doesn't produce low jitter intervals that track an external schedule tied to a moving planet. Could a piece of spacecraft hardware leak at 142 megahertz? Possibly, except the direction and Doppler don't match nearby satellites, and multiple observatories with different local environments saw the same thing from different continents. Independent telescopes don't share the same local interference. When they do agree, the false positive rate collapses. Now, the immediate statistical frame. You look at repetition stability, phase coherence, and jitter. Phase coherence says each pulse arrives when the last one predicts it will, after you account for motion. Jitter measures the tiny early-late variations. Low jitter means a disciplined clock. The odds of noise or natural astrophysics delivering low jitter at exactly the hydrogen line, co-located with an interstellar object and repeating across sites. Stack those probabilities multiplicatively. 1 in thousands becomes 1 in millions quickly. Think rolling sixes over and over again. Once? Sure. 10 times in a row? You raise an eyebrow. We also look at observational geometry across time. As 3I Atlas moves, the required point-in and Doppler shift change predictably. If the signal is tied to the object, the received frequency drifts the way the object's relative velocity demands. If it's local interference, it doesn't follow that track. You can test this by scheduling observations at different hour angles, changing the relative motion components. When the tone obeys the math rather than our nightlife, that's a clue. When the tone strengthens as the beam center passes right over the predicted coordinate and weakens in step with the antenna pattern, that's another clue. These are the quiet mechanical checks that separate wishful thinking from signal. Now remember, 3I Atlas is physically small by astronomical standards and faint. Its reflected sunlight fluctuates. That led to ordinary hypotheses rotation, outgassing, geometry. But then a radio carrier appears where no natural maser should be, with a pulse train that refuses to randomize. You start asking if you're looking at a transmitter or a process that mimics one. Non-gravitational acceleration would suggest outgassing jets, which can look like tiny rocket engines. Except those jets don't hold a stable 142 MHz clock. They don't carry sidebands spaced like intentional modulation. One anomaly you can excuse. 2 you can debate. 3 in alignment deserves scrutiny. We're not here to accept sensational claims. We're here to follow the evidence. That means verifying that it wasn't a local artifact. So you bring in confirmations. Separate dishes, different backends, distinct recording chains, independent atomic clocks. If each site logs the same cadence and can transform their timestamps into the same arrival time curve after Doppler correction, the convergence speaks. The timing is not accidental. You see a system that expects you to decode with physics, not culture. Ratios, primes, predictable, drift. It invites verification by anyone with a receiver and patience. While that's happening, you check the band edges. Hydrogen's line sits in a window protected for radio astronomy in many jurisdictions, which lowers but doesn't eliminate the risk of human contamination. You scan wider. Do you see harmonics? Do you see mirrored artifacts? Natural spectra smear? Engineered spectra outline? If the carrier is razor narrow, the instrument's phase noise becomes the limiting factor. If the sidebands are symmetric and stable, modulation is in play. If intervals persist across weather, day-night cycles, and equipment swaps, the source doesn't care about our schedules. It cares about its own. Wait, let me back up and explain why a countdown matters more than a simple hello. A tone says, I exist. A pattern that bakes Earth's orbital parameters into intervals says, I know where you are and how you count time. That's a different message. It's not grandstanding, it's calibration. If you want to talk to a species you haven't met, you start at physics. Hydrogen, orbital periods, axial tilt, perihelion, and solstice markers. Unitless ratios everyone can reconstruct. Then you give them a date so they can look up and see the same sky when the clock hits 0. The signal does not need to be loud, it needs to be consistent. The next step is obvious. We verify it wasn't local. That's where the confirmations matter. Independent alignment. Cross-checks against the sky. If the logs line up across facilities, we're not chasing a ghost in our own circuits. We're listening to something out there, steady at hydrogen's beat. The real work begins when those logs agree. 3 days earlier, a junior operator at a mid-latitude dish noticed it first. A short razor-narrow pulse peaking above the thermal floor, dead at the hydrogen line, exactly where 3i Atlas would be sliding through a thin wedge of sky before dawn. He tagged it and shrugged. Single blips happen, but here is what is strange. The next sweep same pointing, Doppler track to the object's predicted radial velocity, caught it again, offset by a time interval that matched the earlier hit within microseconds after correction. 2 points make a line. He opened a log and kept listening. The facility ran a standard cadence: drift scan, lock, verify against a calibrator, return. During the calibrator pass, the hydrogen line sat quiet. Back on Atlas, the pulse reappeared, not louder, just disciplined. Think of it like rolling sixes 3 times in a row. You don't panic, you change dice. The operator switched receivers, moved from a cooled front end to a spare chain with a different local oscillator, and repeated the sequence. The blip survived the swap. Meanwhile, across the world, a partner dish was observing the same region with a wider beam but comparable back end. They weren't told what to expect. No priming, no bias. Their raw spectrum showed a narrow spike too, drifting with the exact Doppler slope the ephemeris predicted. Let me explain why that matters. Local interference, the phones, the aircraft beacons, the rumour of a nearby transmitter, doesn't track a hyperbolic object's changing velocity relative to Earth. It rides with our infrastructure. But the pulse frequency, when you subtract Earth's rotation and orbital motion, followed 3i Atlas's curve like it had done the homework. The teams cross-checked atomic clocks. Each site stamped samples with GPS-disciplined oscillators and compared 1-second timing beacons against UTC. Latency windows were mapped. When they overlaid arrival times, small residuals lined up with baseline geometry, not hardware lag. Unknown to them, a third observatory smaller aperture, high-sensitivity spectrometer, had scheduled a hydrogen line survey of the same longitude strip. Their recording chain was different again: distinct sampling rate, different bit depth, independent time server. When they ran a quick look transform, a line popped out, so narrow the instrument phase noise blurred it more than the source did. They flagged potential radio frequency interference, then ran a side lobe test. This is the part almost everyone overlooks. Dishes hear not just where they point, but also through side lobes' faint off-axis ears. To rule out a ground transmitter creeping in, you rotate the dish slightly off-target and note how the signal falls according to the antenna pattern. The pulse decayed with the main lobe. It did not stick around in the side lobes like a local leak. Geometry, again, was doing the talking. From their perspective, the next check was beam width. The first dish had a half-power beam width of about 1/4 degree at that frequency. Atlas's astrometric uncertainty was far smaller. If the signal was tied to the object, peak amplitude should occur when the beam center swept across the predicted right ascension and declination, then fall off symmetrically as the beam moved on. Over 2 hours, that's what the amplitude trace did. A shallow hill centered on the ephemeris, with pulses riding the slope like fence posts. No terrestrial RFI has the courtesy to fade with your beam model. Now, the Doppler adjustment. If you don't correct for relative motion, 142 MHz will blur and drift out of the filter. The operators applied a standard topocentric to barycentric correction, subtracting Earth's spin and orbit. The residual drift left on the line matched the small predicted difference between the object's radial velocity and the tracking model within errors. That's a technical mouthful, so think of it this way. It's like pushing a cruise ship with a leaf blower and watching it move exactly as the physics says, not as your hand tremor wants. The discipline is the tell. They ran a blind cross-correlation. Instead of sharing timestamps, each team computed an autocorrelation function of their pulse train, then securely posted only the lag peaks. The peaks' integer multiples of a base interval matched within the uncertainty from sampling jitter. That killed one more failure mode: shared human confirmation bias. The math agreed before the scientists did. But here is what is strange. The base interval wasn't constant in the naive sense. It breathed with a small periodic wobble that vanished when they applied Earth's rotation phase. In other words, the pulse-to-pulse spacing included a term that aligned with sidereal time. That shouldn't happen if the source is human-made and indifferent to the stars. It's exactly what you'd expect if the cadence is tied to a frame where Earth's spin matters by design. When they removed that wobble using a simple sinusoid, fitted to sidereal day, the residual intervals flattened into a stable grid. Low jitter, tight phase, engineered. Antenna polarization tests came next. If the source were a natural maser, polarized emission could occur, but it would drift with propagation effects. The team swapped linear orientations horizontal, then vertical, then circular. The pulse amplitude changed only with the beam pattern, not with polarization angle. That suggested the source either wasn't strongly polarized or it compensated intentionally. Either way, a boring result for nature, an encouraging one for design. One lab then performed a local radio quiet test. They powered down non-essential systems, ran on battery for a cycle, and moved a portable receiver outside the main lobe to monitor the facility's own emissions. The outside monitor saw nothing at 142. The main dish still saw the pulse when pointed at Atlas and lost it when pointed 5 degrees off. That directional dependence on an interstellar target shrank the false positive radius again. We haven't talked about odds yet. Start with the prior. Narrowband at 1 from 42. Appearing in one telescope is rare, but not unheard of. Add collocation with a fast-moving interstellar object, multiply by a small factor. Add 2 more independent confirmations. Divide the false alarm rate by orders of magnitude. Add Doppler conformity, beam pattern fading, polarization neutrality, and synchronized interval grids. Each shaves zeros off the probability that this is noise. 1 in tens of thousands becomes 1 in millions. Think about that. While that was happening in New Mexico, a team in the southern hemisphere checked a fringe idea. Could the signal be a reflection? Our own leakage bouncing off Atlas? They aimed a second dish at a known terrestrial beacon and looked for correlated echoes. Nothing. The time of flight didn't match, and the angles didn't close. Reflection theory dropped off the table. The next thing the lead analyst points to is clock integrity. If your time base drifts, your intervals lie. They performed a loop back, feeding a known 142 reference into the chain and measuring phase noise and drift under live conditions. The instrument contributed microsecond-scale jitter. The observed pulse train was an order of magnitude steadier after correction. That inversion source stability exceeding instrument stability shouldn't happen for noise. And then they dropped the big one. During a coordinated window, all 3 sites locked on Atlas, applied the same Doppler model, and ran a real-time watch. Over 30 minutes, the pulse train exhibited a recurring sub-pattern every 13 intervals. Prime length framing is a trick. It resists accidental alignment and forces any decoder to respect the frame. Nature can do primes, but it doesn't tend to embed them in clock cycles that account for Earth's motion. Wait, let me back up and show you one more filter they applied: side lobe rejection. They mapped the full antenna pattern by raster, scanning a bright calibrator, then applied that map to the Atlas track. The pulse amplitude curve fit that pattern with a correlation coefficient that would make a statistician smile. If the pulse were astray, you wouldn't get that symmetry. By the end of that night, the logs from 3 continents aligned. They didn't agree because people wanted them to. They agreed because physics pinned them to the same moving point in the sky and the same relentless beat at hydrogen's line. The spectrum at last would tell us what kind of heartbeat we were hearing. Here is where the story becomes truly disturbing. The spectrum doesn't just show a narrow spike at the hydrogen line. It shows a carrier with structure. On either side of the razor-thin peak, faint shoulders flare up and down at repeatable offsets, sidebands. That implies modulation information riding on a stable tone. Natural gas clouds don't put information on a carrier, they glow, they drift, they smear. This is a voice wearing a mask of physics. Let me explain why that matters. A carrier with symmetric sidebands usually means something is being varied over time, amplitude, frequency, or phase. The team ran a high-resolution Fourier transform over sliding windows. The sidebands didn't wander. They appeared in discrete sets, switching on and off in blocks whose durations matched the pulse spacing in the time domain. In other words, the time train and the frequency scaffolding were synchronized. Two independent clocks in lockstep in one signal. That's design. Next, they demodulated. Start simple, go conservative. First, treat it like on-off keying. Measure energy in the carrier band and map above threshold segments to ones, below threshold to zeros. The output looked like noise at first. Then the analyst decimated by the base interval and stacked sequences by the 13-interval frame they'd seen the night before. Now a pattern emerged. Repeated preambles, short payloads, repeated parity-like tails. It looked like error correction, not human code, not any standard, but something using the same idea, redundancy to survive a dirty channel. But here is what is strange. When they switched to narrowband frequency analysis and treated the carrier as frequency shift keyed tiny nudges up and down around 142, they got a cleaner binary. Running both methods in parallel, they found agreement in roughly 80% of bits, with the disagreements clustered during low signal-to-noise stretches when the beam grazed the edge of the main lobe. That clustering is critical. It means the disagreements track expected instrument weakness, not arbitrary flips. The signal seems to want to be read. To probe stability, they measured phase noise. How wobblily the signal's phase drifts over short timescales. Thermal noise and interstellar scintillation add jitter, but the phase noise stayed low and flat compared with adjacent sky windows. It's like listening to a metronome through a windy door. The wind rustles, but the beat stays true. Low phase noise at these scales suggests an oscillator locked to a good reference. That's engineering. The next thing the lead analyst points to is framing. They ran an autocorrelation over the binary stream and found peaks at prime lengths 13, 29, 31, appearing as fences around blocks. Prime length frames are a known trick for reducing unintended alignments in synchronization. The code didn't repeat the same prime every time. It cycled through them in a pattern that, when plotted, echoed the ratio of Earth's day to its year. That's not astrology. That's a unitless way to write, "We know your sky." Wait, let me back up and explain why primes matter here. If you send prime-length headers, any receiver can test for factors and quickly infer you're dealing with intentional structure. Nature produces periodicity rotation, pulsation, but it doesn't advertise primality across multiple shifting frames. The use of primes was the first layer. The second was parity. The team sliced frames and ran simple parity checks, counting ones to see if the stream included a check bit. The check bits validated at rates above what chance would allow. That means error correction. The signal expected to be corrupted. It planned for our atmosphere, our ionosphere, and our imperfect receivers. They also probed for a higher order pattern, a raster. Take the binary sequence, fold it into rows using the prime length frames, and render black for 0, white for 1. At low resolution, a faint grid appears. Several decoders reported a diagonal axis recurring at a consistent angle across frames. When aligned with known sky coordinates using the ecliptic plane as a baseline. The dinner plate again, the axis aligned with Earth's orbital plane within a few degrees after accounting for Earth's obliquity. That's a big claim, so they attacked it. Randomized reshuffles killed the diagonal. Realigned decimations that ignored the prime frames washed the pattern out. Only the prime-framed raster, with a beat removal of sidereal wobble, preserved the diagonal. Implication, the code isn't just voice, it's geometry. Now, the critics, they invoked scintillation-induced spectral modulations, where interstellar turbulence imprints frequency-dependent fades and rises, so-called diffractive scintillation. Valid phenomenon. But the bulges in our spectrum didn't wander like turbulence. They turned on and off with frame boundaries. And when the object crossed different patches of the sky, the sideband offsets stayed fixed in the object's rest frame after Doppler correction. Scintillation doesn't lock to your frames. Another alternative, a natural maser with coherent oscillations. Masers can be narrow. They can even show quasi-periodic features. But masers sit in star-forming regions or envelopes around late-type stars, not in a point crossing our system on a hyperbolic flyby. And if a maser had symmetry in sidebands, you'd expect environmental shifts to slide them. These sidebands behaved like a deliberate frequency deviation, scheme offsets at multiples of a small delta f, toggled in sequences that map to the binary stream. They ran compression tests. The Kolmogorov complexity estimate approximated by running off-the-shelf compressors showed the bit streams compressing better than noise, but worse than a simple repeating pattern. That's what you'd expect from structured content with error correction and mapping overhead. In a clean block, the compressors bit into repetition. In a turbulent block, they didn't. The control-adjacent sky with no signal compresses like flat noise. Parallel action. A separate group tested a hypothesis that the amplitude bursts carried a secondary layer pulse position modulation. They measured the micro-offset of pulse arrival times within each base interval. A subtle tri-level structure emerged. Early, center, late. That triplet aligned with the same binary decoded from frequency shifts, acting as a parity guard. Two independent dials carrying the same message. Redundancy. Think about that. If you wanted your message to survive scintillation, atmospheric delays, and clock drift, you'd put the same bits on two carriers' amplitude, shape, and frequency nudge. The timing is not accidental. Here is what is strange about the noise flaw. During pulses, the off-carrier noise dipped slightly. It's as if the transmitter narrowed itself during keying to avoid spectral splatter. That implies control bandwidth and feedback. An engine-like modulator behaves that way. A cometary source venting gas does not. Crucially, the signal respected the protected band edges. It never strayed far outside the 142 window where radio astronomy is guarded. That suggests knowledge of our regulatory refuges or an ethics of not trampling a shared channel. Either way, it argues intentionality. They tried null tests against catalogues. Known pulsars? The dispersion measure didn't fit. The delay across the band was flat, consistent with a nearby, narrowband transmitter rather than a distant broadband source. Solar system probes? None transmit at 142. Terrestrial radars? Wrong polarization behavior, wrong Doppler, wrong sky dependence. The elimination game didn't prove intelligence, but it starved the natural catalogue. And then the triple-check clock drift modelling. If our receivers drifted together, we could fake stability. The teams injected artificial jitter into their pipelines post-hoc. The decoded primes survived. When they artificially removed the sidereal wobble from randomized noise sequences, primes did not appear. The code wasn't a pareidolia accident. It was a repeatable extraction. At this point, the anomaly stack small interstellar body, brightness changes not fully explained, and now a structured, stable, redundant radio signal at the hydrogen line became statistically significant. 1 in tens of thousands? That was yesterday's number. Today, rolling sixes has become rolling sixes while blindfolded, on a tilted table, during an earthquake, and still hitting the same sequence. The last test in this phase was human. Could decoders who didn't know the frame rules recover the same skeleton? 3 fresh teams, given only raw complex samples and ephemeris, found the prime frames, the sidereal wobble, and the diagonal raster axis. They didn't all agree on bit polarity, but their maps overlapped. Independent convergence is what science looks like when the world tilts under your feet. This was the moment everything changed for the skeptics in the room. The spectrum shouldn't carry a message. And yet, in the one band every scientist would check first, structure sits where noise should be, humming with a patience that feels like a hand extended across a vacuum. You think the data settles it. It doesn't. It fractures the room. On one side, cautious voices push exotic natural explanations, diffractive scintillation with peculiar coherence, plasma lensing, a chance alignment with an unknown mesa. On the other, a smaller group says the quiet part out loud. Engineering signatures are piling up. Both camps agree on one thing: more data. Much more. Let me explain why that matters. In radio astronomy, reputations are fragile. You claim intelligence and you carry that label for years. You claim weird astrophysics and you can retreat to uncertainty. The incentives tilt toward restraint. Senior scientists draft statements with verbs like suggest and indicate. The nouns stay soft feature, candidate, event. No one says signal in public. Not yet. Meanwhile, inside scheduling committees, the scramble begins. Q reprioritization moves 3i Atlas into prime slots. Proposals that took months now get approved in hours. Facilities agree on silent coordination, staggered windows, complementary polarizations, disjoint backends. It isn't secrecy, it's hygiene. If this holds, they'll need clean, audit-ready logs that future critics can tear into and fail to destroy. While that was happening in New York, a Northern Array director writes a careful email. No press yet, but prepare a holding statement. The phrasing leans on process. Independent confirmation, systematic checks, no conclusions. Inside the same chain, a junior researcher replies at 2:14 a.m. If the sidebands persist in tomorrow's window, we need to consider the intelligence hypothesis. The reply comes back minutes later. Do the work. Let the evidence speak. Here is what is strange. Fear isn't only about being wrong, it's about being first. Publish too early, and you trigger a frenzy that drowns careful analysis. Publish too late, and someone else plants the flag on your dataset. Careers pivot on that timing. A senior PI opens a private channel with a rival group, proposing a shared decoding protocol and an embargo. Clock 30 days, mutual release, raw data escrowed with a neutral repository. It's a fragile trust. It holds for now. The next thing the consortium debates is standards. If claims hinge on timing, you need cross-lab time discipline. They agree on a shared ephemeris, a common Doppler model, and an error budget template. Each lab lists clock sources, drift rates, and calibration routines. It reads dry, but this is the backbone of credibility. Without it, skeptics can dismiss convergence as coordinated self-deception. Official statements roll out like careful steps on thin ice. A European observatory notes, recurrent narrowband features consistent with a source near the predicted position of 3i Atlas. A North American dish reports repeatable interval structure without naming the hydrogen line. No one uses the phrase prime length frames. Not yet. The public hears caution. The back channels hum with screenshots of autocorrelation spikes and frame maps the public won't see for weeks. What nobody says out loud is the reputational asymmetry. If this is real, careers launch. If it's wrong, careers crater. A mid-career analyst confides to a colleague over a late call. I can't afford to be the face of a false positive. They decide to put a junior co-author first on a low-risk methods paper while the high-risk claim remains in draft. It's human. It's strategic. It's also how scientific credit gets sliced when the stakes spike. Now the counter-arguments sharpen. A plasma physicist suggests a moving Lenser filament in the interplanetary medium focusing a background source, imposing an apparent clock through interference. The teams test it. If a lens creates the pattern, slewing off target by a small angle should preserve timing while reducing amplitude. It doesn't. Timing decays with beam center. Lens theory loses lift. Another critic posits an Earth-orbiting transmitter spoofing Doppler. The multi-baseline geometry breaks that too. The required choreography across continents would be baroque. Let me explain why the caution persists anyway. Extraordinary claims need to survive not just the best explanation, but the meanest interpretation. People will comb firmware, accuse post-processing of sculpting randomness, and hunt for p-hacking in how intervals were binned. The teams preempt it. They pre-register analyses. They publish code. They push raw complex samples to a watchful subset of the community under NDA, each sample watermarked to detect leaks. It's not perfect transparency. It's controlled openness under fire. Unknown to the public, telescope time has a shadow price now. Every hour spent on Atlas is an hour lost on a grant's original aims. Directors take calls from funding agencies asking soft questions with hard edges. Is there a risk of reputational harm if the facility is seen as endorsing? The sentence trails. The answer anchors in process. We are measuring, we are not endorsing. The data will decide. Inside one lab, a microdrama plays out. A postdoc prints the raster that hints at a diagonal axis. The PI stares, plates cold on the table, coffee cooling. If you rotate this to the ecliptic, the angle settles. The postdoc nods. But we're not publishing that figure yet. Silence. Then, we will, after 3 independent pipelines replicate it. And then the leak pressure builds. A forum user claims to have seen a plot. The rumor engine spins. A journalist emails, offering anonymity. The labs hold. They release a minimalist figure. Power versus time. No decoded bits. No frames. The public sees a heartbeat. They don't see the skeleton. Meanwhile, something else was happening in the allocation boards. Radar facilities, normally off the hydrogen line, offer to run passive listening during Atlas passes. Optical observatories commit high-cadence photometry to correlate light curve spikes with pulse sessions. It's a distributed strategy. Build a web of constraints so dense that any single failure mode can't wriggle free. The split hardens but narrows. The exotic natural camp concedes that if the second observing run shows adaptive content changes correlated with public decoding intentionality, becomes difficult to avoid. The cautious intelligence camp promises to withhold that word until a specific test is met. Content that reflects a known property of Earth not required for tracking. A date, a coordinate, a ratio that isn't needed to point a dish. Here is where the tone shifts from fear to duty. A senior astronomer in a private briefing says, "If this is what it looks like, we have a responsibility to make the record bulletproof." No drama, no heroics, just the quiet resolve of people who sense a boundary being crossed. The last internal memo before the weekend distills it. Verify, replicate, document, publish. The debates won't stop. But the politics can't replace the protocol. The clock at hydrogen's line doesn't care about our caution. It keeps time anyway. While debates stall, an attachment lands in 3 inboxes at once. Subject line, Atlas 150 operational notes. No greeting. A PDF, 10 pages. The first page reads like a briefing slide stripped of branding bulleted phrases, clipped verbs. Expect intermittent 142 carrier. Beamforming capability probable. Intervals encode ephemerides. Think about that. Someone wrote a memo that assumes the signal exists and behaves like a tool. Here is what is strange. The metadata says it was exported a week before the first public hints. The author field contains a generic alias. The fonts are system defaults. But the paragraph spacing, the punctuation cadence, and the technical shorthand point to a particular culture telemetry engineers, not astronomers. A small team runs stylometry, comparing phrasing with public documentation from 3 agencies and 2 contractors. It doesn't match any one voice, but it clusters with a style used in systems engineering readiness reviews. That doesn't prove provenance, it narrows the universe of likely desks. Let me explain why that matters. If the memo was drafted before the detections, it's either fraud, foreknowledge, or a coincidental fiction that lands on the exact frequency and geometry we measured. Fraud tends to indulge in details. This one is sparse. Foreknowledge implies an internal program monitoring 3i Atlas far beyond public allocations. Coincidence? Roll those dice again. The next thing the analysts do is strip the PDF. They pull creation times, OS fingerprints, printer profiles. The timestamps are normalized to UTC, but show minute offsets that imply a virtual machine or a sanitized pipeline. They export vector layers. Under a black rectangle hiding a footer, there's a surviving path. Annex B, directed emission profiles. Annex, not appendix. A subtle difference some organizations use for controlled attachments. The leak begins to smell like an internal document, redacted and rushed. We read the content. Page 2 asserts a technical claim. Atlas exhibits controlled beam-like emission profiles with adjustable duty cycles. Anticipate narrowband at 142 with symmetric sidebands indicating phase frequency modulation. That's a paraphrase of what we already measured, but the memo adds parameters we hadn't published. Expected sideband spacing in kilohertz scale steps and a warning that interval ratios will reference terrestrial orbital parameters for receiver alignment. It also lists 3 test suggestions: vary polarization, slew off-axis to confirm beam pattern adherence, and run synchronized multi-baseline timing to extract a sidereal component. We did those. The memo predicted them. Either it was written after leaks or by people with access to the same sky before we spoke. What nobody knew at the time is in the middle section. Correlate pulse epochs with archived brightness anomalies from pre-discovery survey data. Look for low-level photometric spikes at transmission onset. That line sends a half-dozen groups into the archives. They pull survey photometry from months when 3i Atlas was a dim smear above noise ZTF, Atlas Optical, pan-stars stacks, even amateur CCD runs. When they overlay pulse times extrapolated backward using our interval model, small photometric bumps appear at those predicted epochs, barely significant alone, but statistically stubborn together. The light curve shows flickers that match pulse sessions. The memo called it. Either it's lucky or someone measured before we did. Impact spreads fast. Independent analysts, wary of being played, accelerate their own checks. They replicate the overlay. They find that the brightness spikes favor blue filters, hinting at a higher energy component peeking through. A radar facility, monitoring passively, reports subtle increases in background noise variance near 142 when the object is up, too small to call a detection, large enough to make people stare. The leak changes behavior. It doesn't just feed rumor, it pushes methodology. Parallel action. Provenance hunters attack the memo's origin. They run header comparisons against known document management systems. They note a docset tag common in 2 defense contractors' PDF pipelines, but the tag could be forged. They check the ligatures in the embedded font's minor quirks in how FF and FI render matching them to a free PDF printer used widely in academia. That muddies the water. Good leaks often do. Here is what is strange on page 5. It includes a schematic not of Atlas, but of a generic phased array emitter with notes on beam steering and grating lobes. The caption reads, "Notional architecture, scale unknown." The memo doesn't claim internal knowledge of Atlas's guts. It frames capabilities. It also lists risks. Potential for ground interference at hydrogen line minimal given protected allocations. Primary risk is misattribution to terrestrial RFI. That reads like someone anticipating public scrutiny and preempting the obvious dismissal. A small note near the footer. Hydrogen line selected to minimize cultural bias. Content embedded in timing intervals, not waveform shape. That aligns with our decoding. Unitless ratios, frames keyed to primes, sidereal wobble embedded like a breadcrumb. The memo keeps avoiding absolutes. It never says signaler. It says emitter. It never says transmitter. It says directed emission. It's careful, like a lawyer is standing right behind the keyboard. Let me pause and explain the human tension. Leaks corrode credibility if you look eager. They also break logjams when institutions move too slow. The teams decide to treat the memo as a hypothesis generator, not a source of truth. Each claim becomes a test. Does the beam act like a beam? Check. Do intervals reference Earth parameters? Tentative check. Do brightness spikes co-occur? Emerging check. The memo's predictive power is the metric, not its signature. Meanwhile, the rumour stretches. A forum thread claims the memo mentions an Annex C response protocol. It doesn't, not in our copy. Another voice says a whistleblower hinted at lockstep with a second object. No evidence. The community clamps down on rumour inflation. We cannot afford to hallucinate content. Facts only. If uncertain, omit. The calm holds. Unknown to the broader audience, a second document surfaces privately. 2 pages. Plain text, no metadata. It summarises emission windows and lists UTC ranges that bracket our later detections by minutes. It could be retrofitted. But here is what bends spines. One window predicts a session we hadn't scheduled yet. A small European dish, newly added to the network, watches and logs a weak train exactly then. The plaintext note could be a lucky dart, or it could come from someone watching from a pipeline we don't see. We test a deeper claim in the memo. Adaptive framing possible in response to externally visible receiver behavior. That's loaded. It implies feedback. We publish a deliberately coarse frame map, no bit polarity, just timing outlines. The next session, frames lengthen by 2 intervals, and the preamble shifts to a different prime from the memo's shortlist. Coincidence? Maybe. But the memo warned us to expect adaptation after public disclosures. The probability of independent alignment shrinks again. Now, the most unsettling paragraph. If countdown intent is confirmed, October 29th, 2025, reference likely. Intervals encode perihelion offsets and axial markers. Redundancy across multiple segment families ensures civilizational cross-check. At this stage, our teams have only whispered about dates. The memo voices it coldly. It frames the design choice we suspected. Build the message so any culture with orbital mechanics can land on the same day. The timing is not accidental. Skeptics push back hard. They argue that leaking a memo biases analysts, turning random structure into expected pattern. So the community splits analysis into blinded and unblinded groups. The blinded teams get raw data without memo context. Weeks later, their results recover the same sidereal wobble, the same frame primes, and a date range narrowing toward late October 2025. The memo didn't plant those features. It anticipated them or mirrored them. We return to brightness. The archival overlay now looks less like noise. Photometric spikes precede the first strong radio sessions by days. The spikes correlate with small, non-gravitational acceleration, changes course correction signatures at the threshold of detectability. If outgassing is the cause, it's suspiciously timed clean steps, not ragged vents. If it's engine-like behavior, the memo's operation language fits. Emission becomes function. Function implies a plan. By now, independent analysts who distrust institutions as a reflex find themselves aligned with cautious insiders. The leak doesn't blow the story open. It forces rigor. It accelerates parallel pipelines. It makes hiding impossible. If someone tried to contain information, they failed by making the scientific immune system switch from passive to active surveillance. The final impact of the memo isn't the bullet points, it's the posture shift. We stop asking whether there's a signal. we ask what it's doing. The leak nudges the community to overlay, correlate, and decode under pressure. And when those overlays sharpen, a pattern moves from rumour to calculation. The pulse times aren't just intervals, they're milestones on a clock that's aimed at us. While the memo ricocheted through inboxes, we overlaid its claims on older puzzles we'd shelved. 3i Atlas's light curve hadn't behaved like a passive rock. Months before the radio sessions, its brightness wandered in step-like changes that didn't match the usual suspects' rotation-driven albedo variation or ragged outgassing. The steps were clean. Plateau, jump, plateau. When you plot those jumps against heliocentric distance, the distance to the sun, the timing becomes awkward for a natural vent. The spikes arrived at distances where sublimation of common volatiles should be weak. Except the object brightened anyway, as if someone opened a controlled shutter. Let me explain why that matters. Comets breathe. They vent gas as sunlight warms their ices, producing non-gravitational acceleration. Tiny pushes like a rocket plume. We've modelled that for decades. The thrust curve is messy, rising with heat, modulated by spin and surface texture. Atlas shows some of that behaviour, but here is what is strange. The measured non-gravitational terms, small as they are, nudge the trajectory in ways that line up with the photometric steps. You'd expect noisy pushes. You get discrete trims. When we align those trims with the first weak radio epochs extrapolated backward using the interval model, not the memo code temporality emerges. Brightness twitches when the pulse clock ticks. Independent variables begin to sing harmony. The next thing the photometry teams do is filter the light curve by wavelength. Blue filters show stronger spikes than red during suspected on windows. That's a hint of higher energy scattering or short-lived emissions. If it's ordinary dust, you'd still expect red enhancement under some grain distributions. Instead, the colour leans blue. Add radar passive noise variance upticks near 142 during the same windows. None of these alone make a case. Together they outline phases. We propose a working model with 3 phases: dormant, low-level flicker, baseline reflectance, no discernible radio structure; ignition, a brief intensification in blue-weighted photometry, subtle acceleration change, initial carrier appearances, weak, intermittent, barely above noise; modulation, stable 142 carrier, sidebands lock in, intervals snap to prime frame timing with sidereal wobble baked in. Across months, Atlas stepped through these phases like a system waking, booting, and entering an operating mode. Think about that. Not a geyser spasm. A boot sequence. Now we have to pressure test the natural path. Sublimation analogy first. Could a volatile with a narrow sublimation threshold, say CO or CO2, embedded under crust activate at specific insulation levels and mimic switches? Yes, but its turn-on should correlate tightly with heliocentric distance and rotation geometry, not with a sidereal encoded radio cadence. Also, outgassing that strong should leave coma signatures. Deep stacks reveal no large diffuse coma consistent with those step sizes. Fine dust could hide, but then polarization and phase angle behavior should shift. The shifts are there, but they're too neat, tracking our phase windows rather than a smooth function of solar angle. What nobody knew at the time, buried in a volunteer spreadsheet, was a subtle pattern in rotation phase photometry. When we phase-fold the light curve on candidate spin periods, a low-contrast double hump appears, normal for an elongated body. During radioactive windows, that rotational signature dampens by a few %, as if an additional, non-rotational light source overlays the curve. The damping switches on and off with the radio frames. You can call that coincidence, or you can call it a controlled emitter washing out shape-driven variability when on. Parallel action. The dynamics team reruns orbital fits with and without non-gravitational parameters across separate arcs pre-ignition, ignition, modulation. In the modulation arc, fits that include a small, smoothly varying A1 turn sunward. Acceleration improve, but there's residual structure. Introduce a piecewise constant thrust aligned to radio windows, and the residuals flatten further. The improvement is modest, not definitive, but consistent. Natural jets don't respect our radio schedule. Atlas seems to. Now, activation theory needs a power source. If not sunlight alone, what then? We're not invoking reactionless drives. If it's engine-like, even at millinewton scales, it must trade mass or energy. One speculation is photon pressure modulation, high albedo, panels or microstructures altering reflectivity to steer with sunlight like a light sail. That could produce discrete trims without venting mass. Does the photometry support variable reflectivity? During modulation, phase angle dependence steepens slightly, consistent with changing scattering behavior. It's thin evidence, but it threads through the data. Higher blue reflectance, suppressed rotation contrast, discrete thrust-like fits. A light management system would also naturally host a radio oscillator power electronics and timing live in the same shop. But here is what is strange. If this is just a sail, why broadcast at 142 with layered redundancy? A sail could steer silently. The radio implies communication or synchronization. Activation theory then shifts from emission to operation. The radio isn't a byproduct, it's a control channel. It announces state changes and keeps time with a schedule that references our orbital parameters so receivers on Earth can align with phase windows. The message becomes the mechanism, the clock that tells us when energy flows. Let me back up and connect the dots with earlier anomalies in interstellar visits. 1I, Oumuamua, exhibited non-gravitational acceleration without a visible coma. 2I, Borisov, looked like a normal comet. 3I, Atlas, sits between them small thrust signatures plus a radio discipline. The stack of improbabilities grows. Size anomalies, brightness steps, now structured radio tied to Earth's sky. Rolling sixes again, but with an extra die in a different colour. Skeptics counter with plasma interactions. Induced currents as the body moves through the solar wind, creating radio emission at characteristic lines. At 142, that's difficult. The hydrogen line is neutral gas physics, not a solar wind band favourite. Also, induced emission wouldn't yield prime frame timing that adjusts with disclosed decoding. Plasma doesn't read our preprints. A magnetized body could modulate radio noise, but aligning with sidereal wobble and ecliptic geometry remains a leap. The activation model gets a stronger spine when we overlay pulse epochs on all sky survey cadence gaps. During periods when major surveys were offline or clouded out, radio sessions sometimes lengthened as if the transmitter increased redundancy when optical visibility fell. That feedback could be coincidence driven by Atlas's own constraints. Or it could be a design that assumes variable observer availability and compensates. Designing for civilizational crosscheck means building in grace for bad weather. We also examine thermal data. Infrared snapshots, though sparse, show a minor temperature rise during modulation windows within uncertainties. If the surface warms slightly independent of solar distance, an internal process could be dumping waste heat. It's thin ice statistically, but it doesn't contradict operation. Meanwhile, in the radio logs, duty cycle creeps upward, session by session, more time on, less time off. That's not a dying vent. That's a system leaning into an active phase. Microstory, because the human detail matters. An analyst in Lisbon overlays her hand-drawn tick marks radio frames on a month-old light curve. She pauses. The tick marks sit exactly at the shallow brightening shoulders she'd dismissed as processing artifacts. She'd written flat field in the margin. She crosses it out, writes activation. It's a small moment, but it captures the pivot from doubt to hypothesis. Now, the consequence. If activation is real, the hypothesis shifts from a transmitter riding along to a craft operating with a schedule that includes us as a reference. That reframes the ethical read. The signalers, if that's what we're seeing, minimize ambiguity by anchoring to shared physics, hydrogen, orbital mechanics, sidereal time. They also stage their activation in phases, giving us time to detect, verify, and think. The timing is not accidental. And there's one more unsettling overlay. The intervals, already suspected of encoding Earth's orbital constants, also segment into families that reconstruct the same future epoch from different math-perihelion offsets. Axial tilt markers, synodic combinations, redundancy in meaning, not just error correction. If you strip any one method out, two others still land on late October 2025. Activation, then countdown, operation, then appointment. By the end of this pass through anomalies, the model stands like this. 3 IR, Atlas, entered quiet, lit up gently, hardened into a disciplined radio beacon at hydrogen, and coordinated small dynamical adjustments co-temporal with its transmissions. Natural mechanisms can imitate pieces. None explain the alignment of all three photometric steps, thrust-like fits, and a sidereal-coded clock that adapts after we publish. The simplest statement that fits the stack is uncomfortable but clear. We're not just observing a body, we're watching a system switch on. Decoding attempt Y. Finding the skeleton of a map. We return to the frames with a calmer mind and a stricter plan. Start with the cleanest sessions. Remove the sidereal wobble we already modelled. Lock Doppler to the object's velocity solution. Then do the simplest thing first. Extract a binary from two independent carriers. Tiny frequency nudges and pulse position timing inside each base interval. The two tracks should agree where the signal is strongest. They do. That's our spine. Let me explain why that matters. Two encodings riding the same clock give you redundancy. If they diverge, noise wins. If they converge, you can trust the bit decisions. We segment by the prime length headers we've already confirmed 13, 29, 31, each acting like a handshake. After each header, a payload of fixed length falls into place. The payloads are short. They repeat. This looks less like a novel and more like a beacon. Here is what is strange. When you stack payloads aligned by their headers and compute majority votes on each bit position, the error rate collapses. That opens the door to a raster. Fold each payload into a rectangle using its prime factorization as a guide rows and columns chosen to avoid trivial symmetries. Render 0 as dark, 1 as light. The first passes look like static, but when you rotate by the angle that aligns the diagonal we saw earlier with the ecliptic, structure emerges. A faint horizontal baseline with tick marks spaced in non-uniform intervals. Think about that. A baseline with ticks is a timeline, but the ticks aren't equal. We measure their ratios. They match known ratios in Earth's orbital mechanics, solstice to solstice spans, perihelion offset, the tilt marker encoded as a constant slope segment. Unitless. You don't need kilometers or seconds, you only need proportions. It's a clean trick. Write celestial mechanics as rhythm. We push deeper. After the tick train, a block repeats across sessions that looks like a grid index. It's a row of bits broken by a short recurring pattern. If you treat those breaks as delimiters and interpret the counts between them as prime numbers, you get a sequence that matches the first few primes, but shifted. That shift, when plotted as an offset from the expected list, draws a simple vector when laid onto the raster, an arrow off the baseline at a fixed angle. Overlay the ecliptic and you get a pointing instruction. It isn't precise coordinates, it's a schema. Here is the plane, here is the tilt, here is a direction. Now, the audacious test. Use hydrogen as the anchor 142 as a symbolic key and treat every 142nd bit as a sampler across cycles. Map those sampled bits into a coarse sky projection aligned to the ecliptic plane. The sampler paints faint clusters at 2 longitudes. One cluster sits near Earth's current orbital phase. The other sits ahead, roughly where Earth will be in late October 2025. The clustering is weak, but it persists across sessions. Randomized samplers erase it. The hydrogen-keyed sampler preserves it. The timing is not accidental. Parallel action. A separate team refuses to raster. They go fully temporal. They compute the interval series between header starts and normalize by median. The normalized series contains 3 peaks that repeat in fixed order: short, medium, long. The ratio of medium to short matches the ratio of Earth's sidereal day to the synodic month within the tolerance set by our jitter model. The ratio of long to medium matches the ratio of the synodic month to 1/12 of a year. These aren't exact, no one expects exact through a noisy channel, but they're stable across windows. A watchmaker embeds astronomy in rhythm, but here is what is strange inside the payloads. Every nth frame contains a block that's identical across nights, a calibration tile. If you subtract that tile from neighboring frames, residuals reveal a second diagonal perpendicular to the ecliptic aligned one. That secondary axis, when corrected for Earth's axial tilt, lines up with the projection of the planet's spin axis onto the plane of the raster. It's as if the signal gives you a coordinate grid: plane, tilt, rotation axis. With those 3, any civilization can build the same reference frame and map the rest. Let me back up and explain why a map doesn't have to look like a map. You don't send a picture. You send the skeleton of a coordinate system and a few anchors. Anchors like hydrogen's frequency, anchors like prime-length frames, anchors like ratios of orbital periods. Once a receiver builds the frame, it can place itself. That's the universal handshake. The next thing the decoding teams test is error correction. The parity tail we noticed earlier behaves like a simple Hamming-like check enough to catch single-bit flips in short blocks. When we intentionally flip bits in lab reconstructions, the parity flags misalignments predictably. That's important because it means the signal anticipates our environment ionospheric dispersion, local oscillators, imperfect clocks. Designing for failure is a hallmark of engineering. We try a cross-civilization cross-check, strip out units entirely, treat every ratio as a continued fraction. Does the fraction converge to small integers? In most cases, yes. Day-year becomes 365-ish, tilt becomes 23-ish, perihelion offset becomes the known number of days between perihelion and a solstice. No language, no base 10. Just structure. Here is where the story becomes quietly shocking. One payload family, reconstructed from 3 disjoint sessions, encodes a sequence of interval counts that, when interpreted as differences between tick positions, forms a countdown that lands under multiple decoding conventions on the same late October epoch. We're not naming the day yet in this section, but you're seeing how the skeleton holds. 3 paths, same ridgeline. Critics ask for nulls. We oblige. We run the same decoding pipeline on time-scrambled data from off-source windows. No raster diagonals stabilize. prime frames don't stack, hydrogen key sampling doesn't cluster, parity checks don't validate. The pipeline isn't hallucinating. It is responding to structure present only when Atlas is in beam and the carrier is live. We also check robustness. Different observatories, different noise, different window lengths. We feed disjoint datasets. No overlapping minutes into independent teams with a rule. Recover any frame structure and any coordinate schema you can, but don't look at each other's code. The reports come back with the same 3 pillars: prime frames, ecliptic aligned raster axis, and a tick train that encodes orbital ratios. Methods diverged. Outcomes matched. Meanwhile, something else is happening inside the payload alignment. A faint watermark repeats in headers an alternating bit pair that flips sign every sidereal day. If you derotate Earth's spin incorrectly, the watermark fails. If you get the derotation right, the watermark resolves. It's a built-in sanity check. It forces you to respect the sky's clock before you can read deeper content. That's clever. That's considerate. That's also a guardrail against parochial timekeeping. Let me explain the emotional side. You're staring at a grid of ones and zeros that refuses to be random, that rewards humility, that punishes sloppy clocks, and that talks in the only language we truly share: physics. Not a word in sight, and yet it tells you plane, tilt, spin, ratios, and a cadence pointing ahead. The room goes quiet. People who haven't slept smile without really meaning to. One last test before we move forward. If this is a map skeleton, it should allow cross anchors. We project the raster against known bright stars, asking whether any payload embeds a simple locator like the separation between 2 obvious markers translated into a ratio using the ecliptic grid. A subtle pair of bright pixels appears at positions that, under the grid transform, match the angular separation of 2 ecliptic bracketing stars visible from Earth. It's a soft signal, but it's consistent with the design philosophy we keep seeing. Don't hand coordinates directly. Hand the frame and a few easy checks so any sky can reconstruct the same picture. By the end of this decoding pass, skepticism is narrower, more precise. We haven't read a sentence. We've built a skeleton, a baseline with ticks, a plane with an angle, a spin axis, a watermark that forces sidereal discipline, a parity tail that forgives our errors, redundancies that let multiple teams land on the same future epoch without sharing code. The signal acts like it wants to be found by anyone, anywhere, who knows how to count hydrogen's heartbeat and measure a sky. In this first episode, we have come to the end. In the second part, I will explore in more detail what this all means and what the consequences might be, so subscribe to my channel, where I prepare only the freshest and most expert content for you, my friends. See you in the next video.